Guys, hope all of us are doing fine. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. In my discussion today, I'm going to look at the derivatives via a parameter. And this, of course, is going to be a concept which we are going to come across, especially on the, of course, the various representations of curves, which we said in terms of a rectangular form or, of course, the polar form. And these are going to be various points which we are going to come across, especially for such a kind of what we refer to as a parametric equation. Now we are going to be required to find the parametric equation of a curve that is going to be defined by these two specific points for x and y. And of course, these have been given in terms of those representation for r the cosine over theta and r the sine over theta. Now, in our previous discussion, we have mentioned the concept of a parameter, and I can give this one in example of an hypothetical equation which we can give in terms of y. So let's have, so we can consider, so this is going to be a different set, but we can consider this one for the equation of y defined by the function of, this is specific, of course, the representation of f theta given as such. And we have another equation which is going to be given in terms of x, which is a function of t given as such. So we can have a connection between these two specific equations by having this particular set of value which is going to be common for the two equations. So therefore, if we have y is equivalent to f of theta, and of course we have x is equivalent to g of theta, these two equations are connected by this specific representation for theta, which is going to be given a name of what we refer to as a parameter. Now, in this specific equation, we are going to be having, or in this specific set of equation, we're going to have a way in which we can find a relationship between the two, especially in trying to find what we refer to as the derivative. Now, in a sense, this is going to be giving us a clue on how we can solve such a kind of an equation that has a derivative via this specific, of course, concept of a parameter. And we're going to use this one as one of the examples to give us a general way of finding this specific derivative for such a kind of an equation. So we are going to have an equation that is going to consist of both x and y as functions of this specific parameter that we give as theta. Now, for us to find the derivative of dy over the x given as such, so this is going to be given from the specific concept which we had given as the concept of a chain rule in our previous discussion, and this can be given in terms of dy all over d theta, and this is going to be given as a product of this d theta with respect to x given as such. So if you can say this specific equation, this is going to be basically a product of two, if we may consider to have this specific section of the equation cancelled as such, but we're going just to maintain that one as such for the sake of our evaluation. And as we're going to see later, basically the concept of just cancelling out is going to be eliminating, of course, a lot of information that is crucial for us to understand. Now, in a sense, I'm just going to maintain them as such. So we are going to have this specific case for particularly, I can just give this one for a specific example, whereby suppose we have this y given in terms of 2 the square over t given as such, and we have this x represented in terms of this specific representation for 6t. So we can see that we're going to have a parameter in this specific case, just as we have defined these two specific equation given as such. So if we are required to find the dy all over dx for these two specific equations, so basically we're going to see that we can use the same concept which I've just mentioned up here for us to do an evaluation of the same equation, which is going to be given as dy all over dt times, so we're going to have this one given in terms of dy all over dx of this specific equation is given as dy all over dt times dt all over dx given as such, and this is going to be giving us particularly the product of the two. So if we try to look at this one, is basically equivalent to the dy all over dt divided by dx all over dt given as such. So this is going to be another representation of this specific equation which we can give in this specific form. So for us to find the evaluation for this value for the dy all over dx of this particular two sets of equations, we're going to have the derivative of y with respect to t, which is going to be given as 2t. So we're going to find the dy over dx over 2t, which basically is going to be giving us for the first set of course, a combination for dy over dt. This is going to be giving us a 4t. And for the second case, we are going to have a dx all over dt. And this is going to be with respect to 6t cubed. So this is going to be given as 18 t squared given as such. So for us to find basically the value for this specific equation, which is going to be given as a dy all over dx. So this is going to be equivalent to 4t all over 18 the square of t given as such. So we can simplify this one for us to have the value of 2 for 4. So that's going to be 2 all over 9. And then it's going to be all over t given as such. So this is going to be representing the value for this specific derivative for the two equations given for the value of dy over dx given as such. And this is one of the strategies that we're going to use by borrowing from the specific evaluation we had done for our previous video for the chain rule. And of course, it's going to be assist us in solving such a kind of a parametric equation that consists of what I've referred to as a parameter. Now, in this case, this is going to be one of the equations which we are going to consider for the, of course, gradient of the curve, which has been defined by these two sets of points at this specific value for theta, which is equivalent to pi all over 2. So we are required to find the gradient of the curve when theta is equivalent to pi over 2. And then next we're going to evaluate what is the rectangular equation of this specific curve. And lastly, what is the name of this specific curve. So from the ideas which we have learned, I'm going to reserve the first option for our of course, members. So you can do that evaluation and kindly give us a feedback in the comment section, which basically is going to be the gradient of this specific curve from this specific, of course, evaluation which we have done for the two equations. So we shall look at the second option, which requires us to find the rectangular equation of this specific curve. And we're going to borrow this one from the concept of a magnitude, which we had learned from our previous discussions. So therefore, we shall have this specific equation given for the, of course, value of x equivalent to r the cosine over theta. And then we're going to have y equivalent to r the sine over theta given as such. So these are going to assist us in trying to evaluate for the equation. For representing this two specific aspect of the cosine over theta is equivalent to x all over r given as such, and the sine over theta from this particular equation is given in terms of y all over r given as such. So for us to find the equation of this specific, of course, form, we're going to have the square of the two being represented for the magnitude, as we said, which can be given in terms of the ratio between x all over r, the square of this one, plus y all over r, the square of this one. And these are going to be giving us particularly the ratio of 1. So if we look at this one, if we do a square of this specific function, which is a cosine, and the sine of a square of this specific, of course, the sine, we're going to have identity, which is the square of the cosine and the square of the sine given as such. And this is going to be implying that we are going to have this specific a ratio of 1. So this basically implies that if we have a common denominator for the square of r, then therefore we can have this one given in terms of x squared plus y squared, which is equivalent to r squared. So basically I've taken the common denominator for the two, and I've done a cross multiplication for this specific function of a unit, and we are going to have this particular equation of the curve given using this specific representation, which is going to be basically equation of the curve. And from our study of various representations, so especially on vector analysis, we have come across this specific equation. And this equation is going to be representing equation of a geometrical regular figure that we refer to as a circle. So in this case, this curve basically that is going to be under description is going to be referred to as a circle. And that is going to be forming basically our answer for the what is the name of the curve, which is going to be the curve under reference from this specific discussion. So this is how we're going to be evaluating various range of equation sets which we are going to come across. And kindly check our description boxes for various links of other videos. Engage us in the comment section and also ring that notification bell for a range of other updates on different discussion we do in math, physics, and chemistry, and even in biology and other application areas. So that is it for now, guys. Bye, God bless you. Catch us in our next video.